and you have a review. And remember that if you are an engineer or want to be an engineer or physics major, make sure you do the problems in the textbook. You hide the solution and you have to do it on your own. So whatever comes next, you know, it will be easier to digest. So last time we introduced a new physical quantity and we call it the impulse. So impulse is a kick. Okay, so you can think of this as a kick. It's a vector. Notation is J, right? And the kick, the impulse equals the change in momentum. If there is a kick, there is a change in momentum. If there is a change in momentum, if you run and then you stop, that will produce a kick. Okay, that's this way here. That's how Newton had his second law in Principia. And then if you malax a little bit, then you have F equals ma. But sometimes it's easier to understand conceptually this way. So we did that. Okay, we talked like boxing, you want to roll over. If you roll over for the same change in momentum, okay, so the same kick, if you increase the time of impact, you decrease the force of impact. Okay. And okay, we talked about that. So something which is not intuitive, if something bounces, the change in momentum is always larger because you end up adding the velocity. Okay, so if it bounces, it will take twice the kick, twice the impulse, because not only you have to stop the ball and then you have to start it again. So twice the kick. Okay, so twice the change in momentum. So it's a mistake that people do very often. So when you're going to find a change in momentum here, you will have to add the velocities. You don't subtract, you add the velocities. So bouncing is really bad. So it's like in football, some people who are, they collide with each other. The guy could bounce off. It's going to be more damaging for the brain because the brain has to stop and then bounce in other directions. So that create bruises, right? Okay, so we did that. We can do this one very quickly. Finding the impulse, you can do it quickly. Quick. You wake up. Wake up. No. Wake up. No. Wake up. Okay, so this first thing, you turn that into kilograms from 10. Super Bowl change from 10 down, so initial is down, so that will be minus 10, and then to 10 up. So usually I don't put a minus, but you see it's down, and you can say, okay, up is plus, minus. Impulse is a vector, so I have to be careful, right? So the impulse sometimes is J, sometimes is I, depends, will be the mass, so 0.1 times the final, which is 10, minus 10. Okay, this is the tricky thing that you have to be careful. So it will be 0.1 times 20, which is 2. So Newton second, or you can say kilogram meter per second. It's the same unit. Is that clear? What is the magnitude of the impulse? Yes. Okay, so the time you're gonna, first of all, in that case, that will be, okay, and you use the time if they ask you for the force. So now if they ask you for the force of impact, the average force is the impulse, right? So in that case, the average force times the time of impact will be 2 divided by 0.1, which is 20 Newton. So sometimes they like to give you TMI, like if you take the MCAT, because then students get stuck. What should I do with the time? No, there is no time to find the impact, the impulse. You use the time to find the force. Okay? Is that clear? So the force is actually the next slide. So the next slide, they ask you same question, but now they ask you the force. So in that case, you're going to divide by the time and you get 20 Newton. But sometimes they will just ask you this question, try to confuse students. Okay, but this is TMI in that case. Okay, so we talked about that. When it's his name was Lester Pelton, and he made a fortune with this design here, because when something bounces, okay, it's going to provide a larger kick, right? Bounce back. So boxing, same thing. You have the jab is bouncing off, more kick. My hand hurts now. Okay, so let's move to conservation of momentum. The thing that you have to understand, for every action, you have an opposite and equal reaction. You cannot, but you have the same thing with impulse. For every impulse, for every kick, there is a kick back. You cannot kick more than you are kicking, and you cannot be kicked more than you are you cannot be kicked more than you are kicking, and you cannot kick more than you are kicking. So anyway, for every impulse, the impulse is always the same. The force is always the same, which means that the change in momentum will be always the same, because kick equals change in momentum. So if there is a collision, interaction, if there is boxing, they will both experience the same kick. Therefore, they will both experience the same change in momentum. Okay, so the change in momentum is the same, but you see, momentum is mass times the change in velocity. So it means this one has a small mass, he's gonna bounce back. Consequence is bad. He has a very large mass, so the change in velocity will be very small. It will hardly budge. Okay? So even though when two things are colliding or kicking or pushing, the change in momentum is always the same. One is losing momentum, one is gaining momentum, but the consequence is not the same, because the change in momentum, guys, can go either in the mass or in the change in velocity. So if something is really big, the change in momentum will go inside that mass and it's not going to move. Okay, so a lot of applications here. So change in momentum is the same. Example, typical demo. You take a basketball here, so it's heavy. Basketball is very heavy. And then you have a tennis ball on top of it. Okay, so they are on top of each other and you drop them. Just drop. So what's going to happen? They're going to fall. They're going to be in free fall. So just before they're going to reach the ground, they will have the same speed. Okay, air resistance doesn't have time to do anything because the tennis ball is shield, right? So they both go down, free fall. Baseball hit the ground first, so they're gonna collide heads on. They're colliding heads on. They're colliding heads on with the same speed. Okay, this one has a lot of mass, this one has little mass. The kick will be the same, the change in momentum will be the same, but this one has so much mass that it will hardly slow down. But this one is going to bounce off like crazy. Okay, and you can do that experiment. It's very easy to do, but the idea is that the change in momentum will be the same when they collide. The kick will be the same, but not the consequence. And we're going to see this is called an elastic collision. Elastic collision means there is no loss in kinetic energy. So the change in momentum will be the same and the energy will be the same. So listen to me because it's a trick. When you have an elastic collision, the relative speed stays the same. So in that case, what is the relative speed? Because they move toward each other. So the relative speed will be, from my perspective, if I sit on the baseball here, not only I move toward the tennis, but the tennis is moving toward me. So the relative speed is 2v. Do you agree? It's going to be quick to collide. Quicker than if one doesn't move and one moves. 2v. And when they collide with each other, this one is bounced off. What's going to be its speed? So it's still 2v. So it's going to be 3v. 3 times the speed, because 3v minus v is 2v. Okay, so if the collision is elastic, okay, the relative speed stays the same. And that has huge consequence. Why? Because this one is going to slow down a bit, but we're going to neglect because the change in momentum goes to its mass. This one will bounces off 3 times the speed, so the kinetic energy will be multiplied by 3 the speed for the for the test. If you multiply by 3 the speed, the kinetic energy will be multiplied by 9. Very good. 9. So 9 times the kinetic energy means 9 times the height, because all the kinetic energy is going to go into potential energy. 9 times the height. So that works in that case because this one is so heavy. And then you can explain supernovae with that. Okay, it's like bouncing up. And of course, you have very cool demo. So that was done by, okay, that's here. You have an example.
Check out how high these different balls bounce. Basketball, the super bouncy ball, and the golf ball. Now I'm going to try the golf ball on top of the bouncy ball, on top of the back. I'm going to explain how it's related to a supernova.
Do you see that? 9 times
So
the
here's
height.
golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself,
so you can do that experiment. And so when back then I told my students, okay, you can do that experiment. So someone didn't want to buy, so she went to Walmart. but she doesn't do it right. You should not push, right? You just drop, and then it goes very high. Okay, so this one is a super nice demo. It's a trampoline. So imagine the trampoline is like the heavy one, right? The heavy baseball. So if the baseball collides with a tennis ball, right? The baseball is not going to slow down that much, but the tennis ball will go very high. The change in momentum will be the same. So they manage here to collide the trampoline by doing it in a special way, you're going to see, and someone jumping. So look at those guys in the corners. You see what they are doing? They are colliding. You see? So what they do is when he's about to hit the trampoline, they make the trampoline bounce, right? And collide with him. The trampoline is very heavy. This one is not very heavy. So it's going to go very, very high. So it's a collision between a very large mass and a small mass. The change in momentum is the same, but the momentum change for the guy, I don't know why he has a big belly all of a sudden, and goes into the speed, right? Look at that. Wow. And that was before AI, okay? So it's not AI, it's true. have those videos for a very long time, so you cannot say, oh, it's AI. By the way, I don't know if I show you that. This guy is doing some experiment, and the idea is if you apply a force, okay, during a time long enough, the change in momentum will be huge. So the idea is to have a huge rubber band. He has a projectile here. So the force applies during a very long time. So the force times time equals change in momentum, and his projectile will do as much damage as a gun. I mean, he has like some dummy, and it goes through it. So it's all physics. The other thing I forgot to show you last time, which was cool, is conservation of energy. So in that case, you go from potential, kinetic, elastic, kinetic, potential. How cool is that? Right? So potential, kinetic, elastic, kinetic, potential. Okay, you have to be very athletic, obviously. Okay, so oh, I had another student who did that demo. Uh, Will. So large mass, small mass. So this one is going to slow down a bit, but this one is going to bounce off. The change in momentum is the same, the kick is the same, the consequence is not. This is very bad for this one because it's bouncing up. If there is no loss in energy, the relative speed stays the same. Okay, so it can inspire you. Um, okay, so that's the idea. I found the trampoline one super cool. So the change in momentum is the same, the kick is the same. You can use that when you go to space, if you go to another planet, for example, you cannot take enough fuel. So what you use is called the slingshot effect. So you start from Earth and you pass by Venus. Venus is going to give you a kick from the gravitational pull, right? You are pulling on Venus, Venus is pulling back on you because of the gravitational pull. Consequence on Venus is ridiculous. Same idea. Consequence for you is big. For the spacecraft, the speed will increase by a lot. And you go again, zoom, and you're going again, zoom, and you're going again, zoom. Each time you get a kick, you're going to increase your momentum, and that will be enough to reach Saturn. Okay, right? So it's called the slingshot effect. Same thing with something bouncing off the earth. The change in momentum is the same, but obviously this one is gonna have a huge change in velocity. This one has a kick, um, what is called recoil, right? It will experience a recoil, but the recoil will be tiny because all the change in momentum goes to the mass. Okay. So what's the consequence of this, right? If we go back to Baloo here, consequence of this, so this is Newton's third law, consequence will be conservation of momentum. The total momentum of the system equals to the total momentum before and after. Before and after, they will be the same. Yes. So the mass is not the same, acceleration is not is the same. Is not, and then so I call that number one, and I call that thing number two. Remember thing number one and thing number two. Okay, so what's gonna happen? Baloo. So this is before. So what's going to happen after? So Baloo has a big mass. Okay, so he's going to recoil. And that's thing number one. So I'm going to call that the velocity after. I'm going to use a prime. Don't get upset if I use a prime. Like prime means after for me. Okay, and Mowgli, thing number two, will recoil, right? Big velocity here. So if I translate that, it means Baloo, velocity after minus velocity before equals minus the mass of Mowgli, velocity after minus velocity before. And if you malax and massage, algebra, very easy, you find the following. The mass, the momentum of Baloo plus the momentum of Mowgli before equals the momentum of Baloo after, that's a 1, plus the momentum of Mowgli after. So this is before and this is after. So this is called the conservation of momentum. So you have a system, you neglect the external forces, so it's isolated, right? You can have friction, but it doesn't apply long enough. And you say the total momentum before of the system equals to the total momentum after of the system. So this is called conservation of momentum. It's very easy in 1D, but you have to remember that velocity is a vector, so it could be negative. So it's like you have conservation of energy and you have conservation of momentum, you have conservation of charge, you have conservation of spin, you have conservation of matter. So it's one of the conservation laws. Okay, do you agree? Okay, so the total momentum before equals total momentum after, and we get to collision. Okay, this video is cute. So it's conservation of momentum, right? So just terminology. The momentum is always conserved if you don't have significant external forces, but not the energy. If the kinetic energy is conserved, we call that an elastic collision. If it's partially like elastic, so it doesn't come back to the same place, that means some energy has been lost, right? Because you don't go back to the same height, and right? And in that case here, it's still conserved. The momentum is still conserved, but all the kinetic energy has been lost. Okay, so you don't need to have conservation of energy, but you still have conservation of momentum. So inelastic, elastic. So for example, all those are elastic collision. So you can do that with when you play pool, right? They have the same masses. So what's going to happen if we want conservation of energy? The only way is for this one to stop and this one to go. So this is called there is a transfer of momentum. The momentum from the black ball is transferred to the white ball. So if they are both colliding heads on with the same speed, they exchange momentum. Okay, so the white is transferring to the black and the black to the white. Sometimes it could be in this situation where there is a transfer of momentum. If the collision is elastic, remember this. That will save you time, computation time. The relative velocity stays constant. For elastic collision, the relative velocity is the same, is constant, right? That means kinetic energy is conserved. You can prove that using algebra. You can look at your textbook. So inelastic collision, here is a famous example. I don't know if I have. Collision. Do you see something collision here? So here are some examples. So let's see. This case, they have the same masses. So in that case, boom, momentum is transferred, right? It's an elastic collision. Now they can stick to each other. So in that case, it's inelastic. So some kinetic energy will be lost. If they have the same masses, the speed will be divided by 2. So they stick to each other and they have half the speed. And then you can have hmm? When the inelastic collision happens, how does it decide which direction to go? It's a very good question. You want, when you do the computation, the total momentum before will be equals to the total momentum after. So if two things collide, there will be a winner. The one with the larger momentum will win. Yeah, well, that'll decide the direction. But no, what like in that case, okay, so you have two guys, 100 kilogram, and I cannot remember. There's something back. I don't understand football, line back, back, or whatever back. So anyway, so this one has a momentum of 500. Do you agree? And then this one has a momentum of 300 going to the left. Which one wins? This one. So after the collision, they will move to the right because this one has a larger momentum. However, mathematically, the total amount of momentum will stay the same. So before, it's going to have 200, right? 200 is the total momentum before. It will be 200 after. Which one will win depends on the larger momentum, not the larger mass, not on the larger speed. You have to multiply them. So if this one wants to win, he can add some vest, something heavy to make him heavier, or he has to go faster. So that's how it works. Let's see, I can do elastic again. I can make it, I don't know, heads on. So heads on. So maybe this one is minus. No, this one is 0.2. This one is minus. So minus 0.2. So they collide, they exchange momentum. Now I can make this one super heavy. So like the baseball and the tennis ball. And you see this one doesn't mind. I mean, doesn't but for that one, it's going to bounce off. So it's going to be very big. So usually you do a lab. Did you do a lab like this one? Yeah? It's fun, right? Momentum is fun. You have to do. Oh, that was. I'm behind. Okay. No?
It's because my lab is on Tuesday, so I didn't have it this week. Which means that they have to do it at a later date.
Oh, so they postpone this week or next week? You're gonna do it
I think that they moved that lab to like the
next
not the
Tuesday?
next week, but the week after that one to stay on schedule.
Oh, okay, okay. Okay, so here is an example. I call that hit and stick. Hit and stick. Okay. So let's do so if it's stick, it means that some energy has been lost, right? Where did it go? It went to bruising the brain. Remember, energy is damage, bruising the brain of the little guy, damaging the grass, making noise, hitting. So this is hit and stick. So the final velocity. Okay, so I'm gonna say, so I'm gonna call that before. Okay, so this is before. So the first thing with momentum, you do before and after, and you have to decide which way is plus, which way is minus. First thing. So before, boom, boom. After, they stick to each other. So this one is 100 kilogram. This one is 75 kilogram. I'm going to call him thing number 1, and that will be thing number 2. So after they collide, they move with the same speed. Do you agree? Because, and I'm going to call that V prime. Okay, they stick to each other and they move together. And let's say I don't know. I don't know which way they're going to move. Right? Let's pretend I don't know. Okay, so then you say the total momentum before. So I'm going to say M1V1 plus M2V2 equals total momentum after M1V1 prime plus M2V2 prime. Agree? Okay, so the total momentum before, it's going to be 100, so it's 500, right? So times 5. This one we have to be careful, it's going to the left, so 75 times minus 4, right? Equals 100 V prime plus 75 V prime. Do you agree? Because the velocity after is the same, because they stick to each other. So we have 500 minus 300, and you have 100 potatoes plus 75 potatoes. That will be 175 potatoes, combining like terms. So that will be 200 equals 175 V prime. So V prime equals 15 meter per second. It's positive, so it means it's moving to the left. And I know that because this one is winning, it has more momentum. So this one is partially inelastic. Totally inelastic means they stop. If they have the same momentum, so if I have two big guys, same mass, same speed, boom, they stop. So momentum is conserved, but all the energy is lost to broken bones and damaged brain and noise and whatever. Agree? Okay, so then let's do number B. Okay, so then it says find the change of momentum for each player. So thing number 1, so the change in momentum 1 is the mass of 1, okay, times its change in velocity, which is 100 times the final, which is 1.15 minus 5. So the change in momentum 1 to its mass, right, is slowed down but it's not too dramatic. So minus final, right? So it will be, no, yes, right? So 1.15 minus 5 times 100. So it's negative 385. Do you agree? For number 2, it's more dramatic, okay? Because the change in momentum will go to his change in velocity, right? So 1.15, no, final to the right, okay, minus initial. Okay, so it's a minus minus. So the change in velocity is larger. So it's going to be 385 kilogram meter per second, which means that the change in momentum for the first one equals minus the change in momentum. So the change in momentum is always the same, but the consequence is not, because some goes to more to the mass, some goes to the speed, and the brain doesn't like that because it has to bounce off. That's the unit for momentum. Kilogram meter per second, because momentum is mass times speed, right? Change in momentum could be also Newton second. That will be impulse. It's the same thing. Okay. So you can okay. So they stick to each other. So there is a movie, but a video, but the video that something is wrong, because they say, I mean, the demo is right, but they say that they weight like 1,000 kilogram. I don't believe that. Something is wrong with the mass.
Hurdling or getting defenders for equal. But the lead defender is job.
That doesn't make sense. Do you agree with me? 1,600 kilogram. You multiply by 2, that will be 2,000, 3,000 pounds. Something is wrong. Huh? I know nothing to football, but still, 1,600 kilograms. Something is like, I don't know. It's what?
They switched the conversion, like they
Yeah, but 1,600 pounds.
right.
Is that possible? 1,600 pounds? No.
That's like such an absurd number. No, what I'm saying, maybe they multiplied to get to the kilograms.
Oh, maybe they did a mistake. Oh, maybe they took the pound and they multiply instead of dividing. Maybe that's why. No, because the other numbers make sense, so I don't understand. But the physics is good. The physics is good. Just take one 10. Divide by 10. Maybe, yeah. Ouch.
Size of building, 50 kilogram meters per second. That's the average. 6 meters per second.
Okay, so the idea is that momentum is both speed and mass, right? You can increase the mass, you increase the speed, and then you multiply them together. When there is a collision, the one with the largest momentum win the direction. Okay? It's confusing because I don't know how many back, line back, full back, half back, back. So that doesn't make sense why they are all back. So anyway, conservation of momentum. Okay. Inelastic collision, that means they're gonna stick to each other, right? And kinetic energy is not conserved. Okay, so let's take an example of inelastic collision. So this is like the football, but now you have cars. Okay, you want to try to do it? These these problems are easy when it's in 1D. And then when it gets to 2D, then it's a headache. It's a headache because 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 of the algebra. Okay, so don't look at the solution. So here we're gonna do before, and that's gonna be after, and then we're gonna decide plus is to the right, minus is to the left. I'm gonna call that thing number 1. I'm gonna call that thing number 2. And then I look at the masses, 1,000, so that will be 1,000. So I put a 1,000 here, and this one is 1,500. Okay, they hook together, so that will be the final speed together. V prime equals 4 meter per second. So first step, you decide left is negative, right is positive. You show before, you show after, thing number 1, thing number 2, and then you're gonna do M1 V1 plus M2 V2 equals M1 V prime. In that case, doesn't have to be the case always, but V1 prime and V2 prime are the same because they are hooked together. Okay, so then it's easy. So before you have 1000 times V1 plus 0 equals after 1000 V prime plus 1500 V prime. Agree? So 1000 V1 equals 1000 potatoes plus 1500 potatoes. That will be 2500 potatoes times V prime, which is 4. Is that right? So it's 10,000? 10,000 So V1 equals just 2.5 meter per second. No? Oh yeah, 10. Okay. And to the right. To the right. Yes. And it wins, obviously, because this one is not moving. But the change in momentum is the same, right? The change in momentum for 1 will be equal to the change in momentum for 2 with a minus. And it's not an elastic collision. So that means the total kinetic energy before will not be equal to the total energy after. Okay? I don't know, we can try to do this one. SUV. So it's hit and stick. Okay, so this is before and this is after. So I call that thing number 1, thing number 2. Okay, so SUV, this is 1, 2, 3, and this one is 900. And this one is 15. Oh, they both have the same speed, isn't it? They have the same speed. So it's going to be 15 here and 15 there, except one is plus and the other one is minus, and they move at the same speed after. Okay? So the total momentum before will be 1800 times 15 plus 900 times minus 15. Okay, that's the only thing that is challenging, is to remember that velocity is a vector, momentum is a vector. That's the only thing. Otherwise, it's super easy. And then you have 1800 potatoes plus 900 potatoes. Right? So you do the computation and you get what do you get? 5, yes. To the right. Did you all get that? 5? 5? Yes.
Is the momentum still the same?
So in elastic collision momentum is always conserved. You suppose that it's conserved, otherwise the condition is that there is no external forces. So you're going to have friction, but you neglect them because they don't apply long enough. Now, kinetic energy is not conserved. Kinetic energy is always conserved when it's elastic, so bouncing up. But when it's not elastic, some kinetic energy can be lost, or all the kinetic energy can be lost. So this is inelastic.
What's on?
Inelastic. Momentum, the change in momentum will be the same for both. The total momentum stays the same because you cannot kick without being kicked back, and the kick is always the same. For every action, you have an equal and opposite reaction. That's why it's the same. Kinetic energy can go to damaging the car, it can go to noise, it can go to broken bones. Okay, so that's A. B, the change in velocity for each car. So thing number one, the change in velocity will be final, which is 5, minus initial, which is 15. So the change in velocity is negative 10. Do you agree? For thing number two, the change in velocity will be final is 5 minus 15. So you see the change in momentum is the same. The change in velocity is more for this one because it has a smaller mass. So momentum can go to the mass or it can go to the speed. So the change in momentum is the same, but not the acceleration, not the consequence. Find the change in kinetic energy of the system. Okay, so you have to do that. Okay, so kinetic energy before. So kinetic energy before will be 0.5, the mass of thing number one times the speed, plus 0.5. Thing number two is 900 times 15. Don't put a negative here, right? Because it's a square. And then the final kinetic energy is going to be 0.5, and they move as one. So now we have 1800 plus 900. You don't have to factor, but they move like one, and the final speed is the final speed is 5 squared. Okay, so from here you can find a change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy. And the change in kinetic energy is not zero, which means it's not conserved. And if you do it, I found, I don't know, you can do it 2.7 times 10 to the 5 joules. So it's a loss. It lost energy. Where did it go? It went to sound, heat, breaking stuff, lawsuit, increasing insurance fine. I don't know. So kinetic energy is not conserved, so it's inelastic. Yes. What?
Like if you were to take negative 10 and 20, should it add up to 5?
Negative 10, and so it's not the change in velocity is not conserved, it's the change in momentum. So if you multiply this by the mass and that for the mass, so if you take this times the mass number one and this times mass number two, they will be equal. So the change in momentum is the same, not the change in velocity. Okay, so if I do minus 10 times 1800, that should be equals to 20 times 900 with a negative. So the change in momentum is the same, not the change in velocity. So the force is the same, not the consequence. Consequence is bad for the one with the less inertia. Okay. This one is okay. Can you do this one? How much is lost? So by the way, it's like this. The total amount of energy was kinetic energy, and at the end, At the end, you still have some kinetic energy, so that 1 plus 2, 1 plus 2, but some of it has been lost here. Lost. Heat, broken stuff, noise. Okay. So let's find the final speed, heat and stick, and then we want to do some engineering stuff like ratio. How much is lost? Okay, for those who came late, you have to catch up the lecture and remember that we have a test number 3. I mean, it's not really a test, but it's 10%, so it should boost your grade. But we still have class on Tuesday, okay? We just have this thing that will be open for 5 hours. Okay, so we have a mass M, V, 3M, and that's before. So after, so obviously it will go to the right. So it's heat, heat, and stick. You can see that since now the mass is multiplied by 3, it's not multiplied by 3. The mass is 4 times. 3m and m is 4, right? So it's 4 times. So the velocity will be divided by 4. Otherwise, you say before you have mv equals, this one is not moving, after 3m plus m. So 3 potatoes plus 1 potato is 4 potatoes. V prime, boom, boom. So the velocity after is 1/4 what it was before. Okay, so the change in kinetic energy. So kinetic energy before, okay, it will be 0.5 mass, so mass times v square. The initial. Final will be, you have to add. So 0.5 times 4 is that 4m times the speed square, which is 1 over 16. Okay, which is 0.5 m over 4 square over 4. Yes? So the change in kinetic energy will be 0.5 v square over 4 minus 0.5 m v square, right? So that will be minus 0.5 m 3/4. Do we agree? So we lost 3/4, right? So the change in kinetic energy over the initial energy is 0.5 m 3/4 v square over initial 0.5 v square, which is 3/4. So we lost 3/4. 3/4 of the kinetic energy is lost, so 1/4 is left. Okay. So that's like a percentage, right? So 75% is gone. Yes.
Oh, so K initial, why do you get 0.5 MV squared?
Because the initial velocity here, the initial kinetic energy, this one has no kinetic energy, only this one. So it's 0.5 the mass times the speed square. And this one is like one big stuff glued together. So the mass is 4m and the final velocity is 1/4. So 3/4 is gone. So 1/4 is left. Agree? Think about that. That will be a typical engineering stuff, right? So you need to find the ratio, percentage difference. You divide the difference by the initial. 75% is left. Agree? Think about it. Oh, okay. Try this one. Check if there is a winner. Is there a winner? No. No winner. So what does it mean? 0. Very good. Everything is lost. Everything is lost. So this one has a mass m v. This one is v over 3, but this one has 3 times the mass. So they have the same momentum. They have the same momentum. So they collide and stop. So all the energy is lost. You still have conservation of momentum, but it's lost. Okay, you can show that because momentum before will be mv plus momentum here 3m minus v over 3. So the total momentum before equals total momentum after. So after, you're going to have 4m v prime equals 0, so v prime equals 0. So all the momentum, you can get rid of the kinetic energy, it's all gone, even though conservation of momentum still applies. Why? Because it means for every kick, there is a kickback. Every action, you have an equal and opposite reaction. Agree? Are you with me? So you do that to see which one win, and there is no winner. So we did this one, right? It's a relative speed stays the same. So this one is so big that it hardly slowed down. The relative speed is 2v, so it has to be 2v. So this one is going to bounce off 3 times the speed, 9 times the kinetic energy, 9 times the height. Okay, so we did that before, and that's how a supernova works. Okay, so we did that. Okay, now we did hit and stick. Now we're going to do a recoil situation. So recoil situation is when nothing moves before and then they recoil. So it means it's not a conservation of energy because before there is no kinetic energy and all of a sudden you have kinetic energy, right? Where it comes from? It comes from the gun powder, right? It comes from chemical energy. So this is a recoil situation, kind of makes sense, right? Grandma, lots of cookies, 100 kilogram, little girl, 50 kilogram. They push on each other. The push will be the same. The mass is divided by 2. So what's going to be the speed? Multiply by 2, right? The momentum is conserved. This is called the recoil situation. So in the case of a gun, for example, forgive me, that's an old slide. I hope no one is upset because it's always a classical example in physics, right? So if you have a heavy gun here, the change in momentum is the same, the force is the same, not the consequence, meaning the gun, heavier it is, will have little recoil because all the momentum goes to the mass, but the projectiles here will have a huge speed because the mass is small. Does it make sense? So in that case, we're going to have the total momentum before equals 0. Do you agree? Because nothing moves. So m1v1 plus m2v2 equals 0. Are you with me? Like grandma and little girl, right? They push, so momentum is 0, nothing move obviously, and then you have the momentum after that has to be equal to 0 because the momentum is conserved. Okay, so you're going to say m1 v1, okay, equals m2 v2, and you get to this relationship here. Okay, so I'm going to take examples, but this is the recoil equation. Nothing moves and they push on each other. The push is the same. Okay, the change in momentum is the same. The consequence cannot be the same because small mass, more change in velocity. So if the ratio between the masses is 2, the velocity is also 2. Okay, so I used to show this video. I don't know if I can show it. You don't know what you can show it anymore, but she's not going to be hurt. Okay, so don't worry. She has a magnum, so magnum is very light, right? It's not very heavy, so it has a lot of recoil. So you have to be careful, right? So she's fine, okay? Because for every kick, you have a kickback, right? The change in momentum is the same. In this case, the mass is small, so it has a lot of recoil. So in the military, for example, when you have a sniper, when they learn how to do it, they have to attach the gun to the ground. Why? Because then you increase the mass of the gun by the mass of the earth itself. So now it's like you are shooting with the earth itself, so the recoil will be very small. Okay? But the change in momentum will be the same. Same thing if you shoot with a rifle, you have to attach it to your shoulder. If you attach it to your shoulder, you increase the mass by your own body. And you want to be attached to the earth, so you need a lot of friction, right? So that's the idea. Okay, she was not hurt, don't worry. Okay, so this one, of course, it's a recoil situation. I call that recoil situation. The momentum before equals momentum after, and it's going to be 0. This little girl will have half the speed. Okay, so let's do a typical one. Not a gun. Okay, so these are ice skaters, right? And they push on each other. So you can do it the quick way if you use the relationship, or you can do the long way. I'm going to do the long way and then I will check with the quick way. It's a recoil situation, right? It's like they are shooting each other, right? Pushing. The push is always the same. Okay, I'm going to call him thing number 1. Call her thing number 2. Okay, so that's plus, that's minus. Thing number 1. No, they don't do that. They call him thing number 2. So I'm going to call that number 2. Thing number 2. Thing number 1. That's before. That's after. I call that V1 prime, V2 prime. The mass here is 88 kilogram. Wow, she's skinny, huh? 54 kilogram. We never reach that. 54 kilogram, 88 kilogram. The woman moves away with a speed of 2.5. So 2.5. And you want the guy. Okay? So before M1 V1, I'm going to do it the long way. equals m1 v1 prime plus m2 v2 prime. So they don't move. So the total momentum equals 0, right? Because before v1 equals v2 equals 0. Thing number 1, 54 kilogram, 2.5 plus thing number 2, 88 v2 prime. Agree? So you get v2 prime equals minus whatever. Negative 1.5? Do you agree? Now you can use, for recoil situation, you can use a magic formula, I call that. So it goes m1 over m2 equals minus v2 over v1 prime. It's a magic. No, it's not magic, but it go faster. So you get the same thing. So M1, thing number 1 is 54 over 88 equals minus number 2 is IDK over 2.5, and you get the same thing. So this works only for a recoil situation, not that M1 is at the top here and 2 is at the top. Hmm? No, because you want to make sure that the heavy one will go slower. So it's inverse. So you have V2 here and V1 there. You use this. If you do M1 V1 plus M2 V2 prime prime equals 0, you have M1 V1 prime equals minus M2 V2 prime. So you have M1 over M2 equals minus V2 prime over V1 prime. That comes from there. The total momentum is 0. Yes. Yes, it's an inverse. Twice the mass, half the speed. You can do that. You can go to Miami, they have an ice rink, I think. Yeah, I never been. Okay, what do you think? So half. 100 kilogram man, 50 kilogram women. Are you kidding me? Super skinny here. Okay, so they push back. She will recoil at a speed of 2. Very good, right? She has half the speed, half the mass, twice the speed. Okay, so conservation of momentum has a lot of application. Like if you do a PET scan. So when you do a PET scan, it's so they call it a PET scan. You know, not people to be afraid. Like pet, you think cat, a cat, a dog, a pet. Okay, it doesn't sound so bad. But actually, what's happening in the brain is that you're gonna have two gamma rays, and one shoot in one direction, so the other one has to shoot in the opposite direction. So what you get highlighting. You highlight the brain. Okay, it has to do with a radioisotope using a positron, anti-electron. So the positron goes into your brain, goes with an electron, they annihilate each other. It's going to shoot one gamma ray this way, so the other gamma ray has to go the opposite way because of conservation of momentum. So you highlight the brain. You don't want to have those too much because it's gamma rays, not super safe. So anyway, same thing here, right? You can do the same thing. You see the ratio between the masses equals to the ratio. So there is a recoil here. Any question? Did I lose anyone? No, we good. So a lot. You can have more. We have to. Just I'm gonna ask you questions here, and because we have to do the pop quiz. Imagine you are here and you are not moving, and you have a bag of tennis ball with you. Okay, you have on your skateboard or whatever, giant skateboard, and you throw one tennis ball forward, what can happen to the platform? Yeah, it's going to recoil, right? It's going to move back. Now, let's say you want to be like a rocket man. Was it the song, The Rocket Man? No, rocket. No. Well, anyway, you want to be like a rocket. What can you do to move really fast? To increase the acceleration of the platform? Two things. You can take one tennis ball, two tennis balls, right? You throw them. What can you change? You want to go as fast as possible. So faster, right? So it will be the speed at which you are throwing the tennis ball, right? Speed. What else? The masses, right? So if you take three tennis ball in your hand, you're gonna go faster instead of one. So this is the rocket equation, right? So the thrust of the rocket depends on two things: how fast the fuel is being expelled. Okay, so the speed of the fuel and the mass, right? How much of it every second. And you can show that using, we'll do that next time, using the conservation of momentum. You show that the thrust of a rocket depends, you multiply, when it depends on something, you multiply the speed at which you are throwing the fuel and how much of it every second. So it's a rate, right? How much of it. Okay, so you can do that experiment. You take a tennis ball, right? You do one, and then you do two, and you go slow and you go fast. See if it's increased the speed. So which way you're gonna go in this case? So it bounces off, but you don't catch. You let go, right? So you are not moving before, not moving after the tennis ball moves to the back. So the platform will move. Yes, the opposite direction, right? So if this one goes to the right, this one will move to the left. So now you are moving forward instead of backward. If you catch it, nothing. You're not going to go anywhere, right? So we'll do definitively on the final. You always have the rocket equation because it's so cool. It's explained in your textbook. Always one question, 5 points on the rocket equation. So we'll show you that next time. But you see, the thrust of the rocket depends how fast the fuel is being ejected and how much of it every second. And then you have to take in account the mass of the rocket. So it's thrust mass minus the weight equals that. And the thrust will be equals to that. And then you have to do thrust minus weight equals mass times acceleration. And yes, okay. Okay, let's